Hey everybody, welcome to Physics 1403, Stars and Galaxies. I want to take this video and I want to talk to you about this picture. All right, this is the Hertzsprug-Russell diagram, or just the HR diagram for short. Every discipline in science has its own kind of almost iconic poster or chart or something that goes up on the wall. For example, for chemistry, it's the periodic table, the elements, of course, that list everything. And for astronomy, it is this. It's the HR diagram. And what the HR diagram does is it takes stars and it gives you this huge amount of information if you know how to read them. All right, so I just wanted to talk briefly about this one. And let's just jump right into it. Okay, so first of all, years and years ago, they were taking pictures of spectra of stars. All right, and they noticed that there's all these different lines on them. Our star has them. They're called the Fraunhofer lines. And they came to realize that those lines represent elements that are found in the atmosphere of that star. We don't think about stars having an atmosphere, but we do. And compared to the star itself, that atmosphere may be much, much cooler. So we get an absorption spectrum. And so by looking at these spectra, they were able to get a good approximation of the surface temperature of that star. And this led to them developing a system called spectral classes. Well, then years later, working up in the Northeast, the United States, they took those spectra and they rearranged them because they were just kind of haphazard, right? And a bunch of ladies working at Harvard, I think it was. If you ever see the play Silent Night or Silent Skies, this is what this is about. Anyway, where they start looking at all of these different spectra and they realized that the pattern was wrong originally and then they rearranged it. All right, and they ended up with, they just gave them letters and it was O with the hottest stars. And these stars, even the only thing you're going to find is ionized hydrogen, and it's going to be a very weak hydrogen signal. B is going to be a strong hydrogen signal as it cools off, right, all the way down to A, F, G, K, and M. All right, and all the other letters were unnecessary or just in the wrong place, and so they threw them out. All right, and to help us remember that, astronomers for many, many years ago have said, "Oh, be a fine girl, kiss me," or "Oh, be a fine guy, kiss me." All right, either way, that's how we would remember them. So then they began, so this is our x-axis on our HR diagram, is the spectral class. And so what we have is high temperatures on the left, which is a little unusual. Normally you have high numbers on the right. So you have your highest temperatures on the left and your lowest temperatures on the right. And so you're going from these very high 30,000 Kelvin down to less than 3,000 Kelvin. Just as a reminder, our Earth is about, or our sun is about 5,800 Kelvin. So we are right about here. We are a class G star. All right, and so what happens then is then they began charting luminosity. Now, remember, luminosity is not brightness. Brightness is kind of a relative term. Remember, you have a flashlight that is close by and a star that is billions of light years away or hundreds of light years away. Obviously, the flashlight's going to appear brighter, even though in all reality, we know it's not. All right. Luminosity is how bright is it, or what's its energy output. And they measure that in terms of solar units. Our sun is 1 solar luminosity because that's something we're familiar with. We do the same thing with mass, by the way. When we measure how big a star is, instead of using grams or kilograms, we often use solar masses because we're most familiar with our sun. So we'll say it's 2 solar masses, which means it's twice the weight of our sun. Or 10 solar masses, or 10 solar radii. That means it's 10 times the radius of our sun. All right, and so when they began graphing this with luminosity on the y-axis and temperature on the x-axis, they began to see a pattern that formed. And I think the most important part of that is right here, which they call the main sequence. Most stars, 90% of the stars in our galaxy, and understand that every star that is visible is in our galaxy. We don't have the technology, we don't have the telescopes that can pick out individual stars in distant galaxies. So any star that is on this chart is in the Milky Way. All right, so we start over here with something like, for example, Altair. Altair is a type A star, so its temperature is probably somewhere around 8,000 Kelvin. And then we come over here and its luminosity is about 10 times of the sun. And so pop, they put it in there. And so some of the things they began to notice, first of all, like I said, about 90% of the stars, and obviously it doesn't have all of them, 90% of the stars are going to fall on this they call the main sequence. And they've since come to realize that the main sequence stars are all stars that are fusing hydrogen in their core still. Okay? And so you come down here, some of the smallest stars like Wolf 359, which if you're a Star Trek fan, you know that's where the Federation got beat up by the Borg. Good to see them get a little bit of actual astronomy in there. All the way up to some of these some of these stars like Spica and Bellatrix, and so these are some really huge stars. And so one of the things they start doing is, so you have this main sequence. And then you have over here this branch called the red giants. All right. And they're red because they've cooled off. This is, and I joke about this in class all the time, that stars have a life. They have a birth, they have a life, and then they have a midlife crisis. This is the midlife crisis branch. This is the giant branch. When a star, particularly a star that's in this mass area here, reaches a certain age, and when they start expanding or expending all of the hydrogen that is in their core, all right, then they will undergo some changes, and they will become a red giant. And so we have this area over here. And one of the things that jumps out, or should jump out, is that these red giants are not very hot, but they're very luminous. That's how we know they're giants. Because they're luminous because they have such a huge surface area. They're not luminous because they have such a high temperature. In fact, every one of these are cooler than our sun. So when you look at something like Aldebaran or Pollux, Arcturus, the bear, all of these things, these are all giants that are past a certain age in their life. Then you have these supergiants up here called, those sometimes called asymptotic giant branch stars, or AGB stars. All right, this is Betelgeuse and Altairus. All right, Betelgeuse is right. It is going to die very soon. I don't know how to say it, but it's going to die soon. Now, astronomy terms, soon could be anywhere in like next million years. But anyway, so it's this huge, incredibly bright star. In fact, it's the brightest star in the constellation Orion. And yet, when you look at this, its temperature, it's a class M star. It is a class M supergiant. It's just that once again, it is so bright because it has such an incredibly high surface area. So when we start looking at this, just like the periodic table in chemistry, if you start looking at this, you start picking out more and more information. For example, this one, I don't know if you can see it on the video very well, this one also has radii in it. For example, right here, this line coming down here tells us the star's radius. And again, the sun is one solar radius. That makes sense. All right. But some other stars that are pretty close are like Centauri B. It's really close. Centauri A is really close. All of these things, so they're kind of like twins of ours. SETI is pretty close. So we can see, and once again, look at that. That radius falls into a very specific pattern. Another thing is that surface temperature, mass. The mass of a star is directly related to its temperature. And so when you start over here, this right here would be a 60 mass star if we could find one. This is Beta Centauri. It is a over 10 solar radii, and it is a super massive, about 20 mass star, 20 solar mass star. And so you can see over here, although they don't draw the lines, which I appreciate because it gets really confusing after a while, is you can also tell the mass of that sun or that star. All right. For example, Betelgeuse is super big, but again, it's because it's so big, it's lost a lot of its mass. All right. And then lastly, on here, written in green, is the lifetime. Our sun's going to have a lifetime of about 10 billion years, give or take a little bit. All right. It's got that much hydrogen in it, and it's that temperature. Very easy to just start calculating these things out. Right? But the more massive a star is, for example, when you get over here to like Spica, Spica's only going to have a lifetime of about 10 to the 7th years. That's about 10 million years. So it's going to die, use up its fuel, even though it has 15 times more fuel than ours. It will burn through it 10 times faster. And so all of these are things that you can tell from the HR diagram. All right, so HR diagram, I guess in short, is just, it's one of those really useful tools that you can tell a lot about the stars that you're looking at in the night sky or through your telescopes. And you can also get down here, by the way, here's this area we didn't talk about is the white dwarfs. We'll talk about those. Those are actually the burning corpses of dead stars. Those stars have already died. And so you can you get an idea of so much of this information is available on the HR diagram, making it one of the most useful tools in astronomy. All right, so I'll talk to you again later. And until then, have a good time.